Hello, everybody. It's Sam, the Reclaimer developer, and while I've been working on It Flies By, I've been thinking about development strategies for refactoring the engine for the Reclaimer because I know it's sort of reaching its limit as far as what I can expect it to do in the current way it's being developed. So, um, these are just some ideas I've been thinking about that I would like to come back to at another point. And if it gives anyone else some inspiration or ideas, I thought I would just sort of record what I was thinking about. So this isn't going to be extremely technical. I'm not going to be going over too many numbers or like code or anything like that. Just some ideas that I had. And so this is some ideas I had for fault tolerant game engine routines, and specifically how ideas on how to maximize hardware potential. So let's go over some fundamental laws here. These I call these laws because these cannot be broken, and not all. Nothing's here like my idea. These are things that I've just sort of piecemeal kind of brought together from various talks or papers or presentations that I've seen. If you've seen Mike Acton's presentation on data-oriented design, his thing that he says repeatedly is data does not exist in a vacuum. What that means is every byte of data in memory is adjacent to other bytes of data. And whenever you spend time to read that byte, you are also reading a certain amount of adjacent bytes. It's something that you are not, it is something that's inescapable. And this is something to really consider on systems with caches, and pretty much every modern computer has at least an L1 and an L2 and even sometimes an L3 cache. But the caches that we're concerned about is L1 and L2, specifically L2. So second, no operation is free. Pretty much the only thing that's free on a CPU is reading from a register, data that has already been preloaded into registers that the arithmetic logic units are going to be using to do math operations. And spoiler alert, if you do a analysis of your program to see like what is the most commonly used set of instructions, it's not going to be reading from a register. It's going to be things regarding loading data and prepping data, getting it into the registers, and then doing the transforms on that information. And all of those things, everything else is going to cost a certain amount of cycles to complete. It's going to take time. Even if it's a small fraction of time, it's going to be required. And third, resources are finite. I don't care what system you're working on. You could be working on the most powerful resource heavy system that's ever been built by man. The most powerful computer still has a finite set of memory and performance characteristics. There is a maximum CPU speed that it can run at. There is a speed that it takes to read memory into caches. And every single computer that has ever been built or ever will be built has a limit of work that you can actually do the math and calculate before it just sort of keels over and can't handle it anymore. Even if that's a massive amount of data, a massive amount of transforms, you can still put a number on it. So with that, let's keep going. So maximizing potential, what does that mean? Well, if you're manually managing a fixed block of memory, you always know how much memory you have to work with per frame. And so this per frame idea is what we're going to be sort of like building this around. If you know the speed of your processor and cycles per second, that's gigahertz is billions of cycles per second, megahertz is millions of cycles per second. Then you can sort of do the math on calculating cycles per frame. How? If you that means you can take the processor can do this much cycles per second. I'm doing like 30 seconds per frame. You can just do plug and chug math on determining what your theoretical number of cycles you have to work with is per frame. If you know how many cores your processor has, you can set aside extra cores for processing work involved in producing a frame. If you know how big the L2 cache is, you know how much memory you can work with before you cause a cache miss. And in terms of like what is the frame rate that you want to set at, like what should be the target, it should be something that's harmonious with the refresh rate of your monitor. There's if you for an optimal experience, you want to sync with that as much as you can. And this is all stuff that we can calculate on Program Start. You can go like that, and you can produce a theoretical set of performance characteristics through a set of very simple function calls, or system calls rather. And as the game or the engine is running, you can fine-tune these metrics. So you can do some things that can calculate what the actual performance characteristics are and how far they deviate from your theoretical limits. And if you're constantly reducing like the actual performance, like if it's constantly getting further and further and further away from your baseline, you know that you have a problem somewhere. And so let's go over what we consider hard system constraints, things that we are not going to be able to get away from, or things that, we just deal with. First of all, memory is mostly cheap these days. Back in the day, a couple of megabytes of memory was really expensive. I remember when I was in high school, there was an Apple II in our computer lab, and it had a 10 megabyte hard drive. That hard drive was as big as a inkjet printer. It was huge compared to what you consider a hard drive to be, and it was 10 megabytes. And the power consumption on it was so intense. There was a cobweb inside of it, and it caught fire one time. So but it still ran. Like it was a beast that withstood the test of time. These days, memory is really cheap. You'd be hard pressed to find a laptop or a desktop that had less than 4 gigabytes of memory today. If you don't have enough memory for what you're doing, you can just request more. But that's provided you're using the memory well. If you know what you're doing, if you're requesting more than, whatever the platform is, if you're requesting more than half of that platform's available memory, you're probably using too much. And this is all within reason, right? If for whatever reason, someone with a Windows XP machine with 128 megs of memory said that they wanted to buy the reclaimer, there's only so much that I can do for you, right? That's just kind of unreasonable. But here is something else. CPU cycles and cache sizes are fixed. They are written in stone, and there is nothing that you can do about it. You can overclock your processor, and you can get a little bit more in terms of cycles that are available to do a certain amount of work. But for the most part, it's still within, that ballpark of whatever its, baseline is. We're never going to hit 100% utilization. CPUs are doing all kinds of shit, in the background. So there's an operating system that's running. Your operating system, especially, after the days of Windows XP, is doing all kinds of crap in the background. It is context switching between, 500 different processes, and, since the days of Windows XP, operating systems are extremely inefficient, especially Windows ones. We're never going to hit 100% utilization, but we can calculate a reasonable, best guess as to what we think we can do per frame. And just sort of a baseline, kind of obvious thing, if the amount of work we're doing exceeds the processor's speed, so for instance, if the amount of work we expect to do in a second is more than, the cycles per second of the processor, the game is going to suffer in terms of performance, especially if we're doing that repeatedly. So by far, our biggest bottleneck, provided we're using memory well and we're using CPU cycles well, the L2 cache is going to be our biggest bottleneck by far. Every time a cache line is evicted, that is a mandatory 200 plus cycles just to refill it. On some machines, it would probably be a little faster. Other times, it could be slower. But this is sort of what we can expect an average to be. And when you do that over and over and over and over, it is cache misses per frame that is going to be your biggest bottleneck. So what our intended goal is to maximize the amount of cycles per cache line read. And again, this is all within reason. If for some reason they're using like a Pentium from, I don't know, 2003 that only has, that's measured in megahertz and megabytes, there's only so much that we can do. Like, within reason, like within the last couple of years, there's no reason that any platform, modern platform, can't run the systems that we're building. And in these game systems, the frame is enforced. And a frame consists of two outputs that the player can perceive. One is graphics, and the other is audio. These are written in stone, and we will never, never, never prioritize anything above these. We will always ensure that the game engine hits the frame and renders what it has available. So that means whatever amount of work is queued up to be done, it is always going to leave bandwidth for how many cycles it thinks it's going to need to deliver stuff to the graphics card and the audio out. If we miss a draw call or processing audio, the game's going to stutter, and that's going to lead to a negative player experience. And there's going to be a core engine thread that essentially batches up all the draw calls, batches up whatever audio is going to be rendered out, and it takes care of that. We can approximate how much time, how much memory it's going to take to deliver all of those things. And if we subtract that from our theoretical baseline, we have, this is how much extra work is available to do per frame. So if we know that, we can batch things into work groups because we know our theoretical performance and the mandatory amount of work it's going to take to deliver a frame. But now there's the actual game stuff that we got to do. So, like, if we were just doing this, we would just be rendering, just noise to the audio out and just having a blank screen being rendered through the graphics card. So, and this is all assuming that we have done a good job of managing our memory. We should be able to batch all of those work groups together. So, for instance, if I have a bunch of entities that need their positions updated, I'm going to batch them all up and do them all at once. And if I have a bunch of things that need their rotations updated, I'm going to batch them up and do all of those at once. And if we can also do some math on, like, what's the operation that's taking place and what's the data it's working with. We can determine how big a work group is, like, meaning how many of those things in memory can it process before we hit a mandatory cache reload. So we bundle those things into a work group that we know will completely fill a cache line. Those cache misses will kill performance by far. We don't want to miss them. So now we know how many cycles and how much memory it's going to take to process one work group. And if we know that, we can determine how many work groups that we can process per frame. Now, this is going to depend on what the actual work the game needs to have done. But we can, this is like reasonable, like, best guesses. So, depending on the work groups that are being done, we can sort of like do a best prediction of how we're going to use the resources that are available. And now that we've batched everything, we got to actually process them. But remember what I said. The core thread is always going to prioritize delivering the frame. The frame rate is enforced. Whatever we have calculated, that is what we are going to do. We are always going to draw at that rate. We are always going to render audio at that rate. And the core thread will assist in processing work if it has the bandwidth available. If it doesn't give a shit, like, if there's extra work to be done. It will always choose to postpone work if it means it has it hit its limit in terms of, like, I still have to deliver this work to the graphics card and the audio out, and also, like, respond to user input and other critical things that it has to do. Like, it will always take the work that is left to be done and put it off to a later frame to pick it up at another time. So modern processors have multiple cores, so let's take advantage of them. So if we have multiple cores, we will always have just one thread available per core. And by default, we're not going to have more threads than we have cores. You can spawn as many threads as you want. You could spawn like 500 threads. But you're going to start running into performance issues if you exceed the number of cores that it has. There's just going to be way too much context switching going on. And so if we calculate how many threads do we need to just run the basic operations of the game, the core threads that are picking up and processing work and delivering them to the player. You could probably hear my daughter laughing in the background. She's doing okay. She's just with her mother. Whatever threads that we're not using are free to process work. And so that means whatever our cycle budget per, remember that theoretical limit versus like actual limit, that's going to be chewed up by the core thread's mandatory processes it has to do. But now we've essentially taken that and freed all of those cycles up to be processed by these job threads. So, hooray. And we can also schedule future work. Like I said, how we can push work into the future. We have a lot of information. If we've done everything right up to this point, we've got a lot of info on how much work we can do per frame, provided that it's accurate. But what happens if we have a ton of things to process? Well, and like an example of this would be like, I don't know, if I'm simulating, the planet, and I have just hundreds of thousands of entities that need to be updated, well, it's unreasonable to expect that I can do all of them in one frame given the amount of threads that I have. Well, what we can do is we can incorporate a scheduler that can sort of take a peek at what the amount of work the worker threads, the core threads, and the spare job runners, the red shirts, basically, how much work how much bandwidth they have available to do work now and a certain amount of frames into the future. So you can set a reasonable amount. Let's say like half a second worth of frames, or like 15 frames, or something that you set. This is how far ahead we're gonna look. You don't want to look ahead too far because that's just resources you're also gonna be consuming, and we just reasonable amounts, right? So we set a reasonable amount of how far we're gonna look ahead, and we determine where we can sort of assign work to a specific job thread to a specific frame. And if we're constantly still like exceeding that amount, like we are filling up all of those like future work groups, we know that we can reasonably expect that, hey, we're asking our engine to do a little too much. So let's recap. We're talking about all the things that we can do, right? We can calculate the resource requirements. We can calculate theoretical versus actual performance. We can calculate hard limits of work we can do per frame. We can diagnose problems that come up and continue to fine-tune work groups. And we can always meet the frame without stuttering. Lo and behold, therefore, we can do anything when we know our platform. So, how do we do this? Like, what does the architecture behind that actually look like? Well, to do that gracefully, there's at least 3 threads that we need, or that we would like to have. One is pretty much obvious. We have the game window. So this is like the window handling system that's responding to operating system events like key presses and things like that, and it's essentially the parent thread. It holds the game logic. It's the thing that does the main game loop that you've probably seen 1,000 times in every how to write games, textbook, tutorial, whatever. Then we have the job scheduling thread. That thread is going to be intercepting requests that the game makes. Things to spawn, things to update. It's just going to be making requests willy-nilly. And the job scheduler is going to tell us if it's able to turn those into a job, when that job is going to be executed, or if we're asking for too much. And then we have the core thread. This is the Wumbo thread, the one that does everything. It is always going to prioritize rendering, but it will do work when it has bandwidth available. And any remaining cores that we have are going to be assigned a thread that is exclusively going to be processing work. And depending on the system architecture, like maybe the user has a dual core processor, we may have to consolidate these things. But we're going over like an ideal scenario where we have at least a quad core processor where we have those 3 core threads and we have at least one thread that we can use to process extra work. And all of these settings can be overridden. Like if they want to say, hey, I want 16 job runners on my dual core processor, you do it at your peril. If they insist on doing this, performance is most likely going to suffer. This is about doing our best to provide a best guess as to how to utilize the resources that are available to us. This is like, we're confident we can deliver the frame in this amount of time. And if the player chooses to unlock that and, change some things, more power to them. But we can no longer guarantee frame delivery. Let's see. Can I move? I can't move that anyway. So game logic and window handling. That's what the word says. So that's the first thread. It's the game executable itself, mygame.exe. So program start. We have a core loop that manages the game logic and the game window. And the game is going to use a series of API functions to issue commands or requests or queries to the game engine that, it needs to process the scene that it's currently working with. And the job scheduler will tell us basically how much of a load we have our game engine at. And if we're at capacity, it'll tell us, hey, you got to stop. I'm at capacity. You got to slow down. And thread 2 is the job scheduler. This is the one that tells the game, hey, I'm ready to accept requests. Give me what you got. And the job scheduler accepts these requests and will batch them into work groups that are sorted by priority. And they're assigned to a frame and a job worker that they will be executed by based on priority. So an example of like a high priority system would be updating entity positions that the player is interacting with. Like if the player is going to have a position and the enemy they're shooting at is going to have a position, those are critical to update according to the game logic. But if there's like a tree in the background and there's like particle simulation on the leaves because there's wind blowing, that's not really considered a high priority system because we don't want to prioritize that over updating the player and entity positions because the player is going to be focused on those two things, not necessarily what's going on in the background. It'd be nice to have everything running, but we may have to prioritize things. And the job scheduler is going to let us know if we're asking for too much. Like basically if we're constantly overshooting the bandwidth of resources that are available. And so we can also accept user input here. So we would essentially have to be able to process immediate interrupts. We want to deliver stuff to the screen, but as a second, if the user hits like pause or something, we want to be able to stop what the game's doing so that we can let the show the user that the game hasn't hung up, basically. Like there's this really hilarious video of like something like 100,000 or 1,000 miniature nuke mines going off in Fallout 4. And it's like they shoot one mine and there's a chain reaction that sets all of them off and the game locks up. Like it can't even anymore. And every time they load it, it's constantly loading into that state, right? The game will lock up and they can do nothing. Well, I would also, if it's possible, want to prioritize user input where the game can just stop what's going on, pause all the threads, and prioritize user input. If we can handle interrupts, the player can essentially exit out of a game without actually, like, task manager, right-click, close. Yep. So now we get to the core thread. This is the worker. This is the one that's carrying everything. We can process work groups here. Like, it is going to be processing work groups. But we're prioritizing audio and video. We cannot misrendering or the frame is missed entirely. We've missed it. We failed to hit our requirement. We have a finite amount of data and audio and draw calls that we can make here. Calling system resources, basically making calls that have physical manifestations where it's like rendering stuff to the graphics card or rendering stuff audio out, that's expensive. Especially rendering stuff to a graphics card. We want to, of course, this is all assuming that we are utilizing our draw calls well. We're batching things up and handling more than one thing at a time where it's possible. We want to limit the amount of draw calls, but the amount of draw calls that we have to make is going to change based on the work that we're assigned. So the job scheduler is going to do its best to give us stuff that it's confident that we can handle based on our initial calculations. And then we got the job runners. These are the red shirts, basically. So all they do is process work. They just do busy work. We just try to keep them busy. Anything that's left, any cores that are left, we give them a job runner thread. And we don't care about graphics. We don't care about audio. We just fill the tables for rendering. Like, hey, the core thread is going to pick these up, and we just try to fill it up with as much stuff as we can. So, but the idea is we want to keep that core thread as free as possible to process those graphics and audio calls. That way, we can fit in more expensive stuff to do. And like examples of that would be like ray tracing or cloth simulation, water simulation, particle simulation, compute shaders, and stuff like that. So anything that would involve expensive graphics calls, we want our core thread to do those because our job runner threads are keeping the bandwidth on it as low as possible. And so here's an example of what a typical execution would look like of a frame. The game processes its logic. It has a scene that it's processing. There's a set of things that are going on, and it's basically issuing requests as fast as it can. There's no delays. It's like, I want to do this, I want to do this, I want to do that. And it's doing it as fast as it can. And at the same time, it's doing that. It's filling up requests like crazy. The renderer is outputting the frame right now that the user is looking at. We're going to call the frame that the user is looking at T0 because it's at time 0. The scheduler is sitting in between the game and the engine, and it's accepting jobs for T1, not the current frame, but the next one, up to however many frames we're looking ahead. Essentially, we're treating this like a pump. We've got a pipeline, and there's a pump that is just constantly moving work through it. We want to keep the core thread primed with as many frames of work as we possibly can. This means our logic must be at least one frame ahead of the render and be as fast or faster than the frame rate. Because if we don't hit it, we already know that provided that we guarantee frame delivery, the slow part is going to be the game. If we are unable to complete our loop that sends requests to process the scene, we're going to starve that thread of work and we're going to miss our frame. But it's going to be on the game side, not the engine. And when I say we can use immediate mode style logic, there's if you look at the library for I'm GUI, immediate mode graphical user interface, I think the standard de facto one is Dear I am GUI. You can look it up on GitHub. It's a popular graphics accelerated GUI library that uses immediate mode logic. And there's also a presentation by Casey Muratori he gave, I think, in 2006 or 2007 on what he means by immediate mode. So basically, we just want to keep decision-making as low as possible. We just want to just issue stuff and try to keep the amount of processing, amount of logic, amount of number crunching that we're doing in the game as low as possible. We want to just be issuing commands as fast as we can. And in an ideal world, that means we're running through the game loop much faster than the frame rate. So we process the game loop as fast as physically possible. And the thread that's rendering stuff in the background is like, what work is available, process it, render it. What work is available, process it, render it within the constraints of the frame. So basically, we want to put together requests faster than we can process them, as long as it doesn't mean the game logic is going to lag. And if we have an API method to let the scheduler know when I've started my game loop that processes the scene and when I've ended it, it can tell us, if we're close to that baseline or not, if we're staying ahead. If we're consistently undershooting, like if we're constantly missing it over time, we know that the scene we're trying to process is way too big, and we need to split it up into smaller scenes. And if we're constantly overshooting it, which means that we're running so fast that like the scheduler can't keep up with us, we can do more stuff. It's like we're constantly overshooting. We're not even like delivering or rather we can't keep up with the scheduler. I had it backwards. The scheduler is constantly asking for word. Give me word. We got a frame ready. And the game is just like, oh, wait, hang on. I can't even give you that much to fill up. You're not even filling up one frame worth of work. Well, we know that the game can either do more stuff or we can scale back. We don't need to have as many resource-intensive processes running because we know we're not going to fill them. So why put all this effort into, like, reasoning about, like, the platform and all that kind of stuff? Like, this is a ton of stuff to consider. Well, a lot of games today are exclusive. You can have a decent computer. Like, this computer I'm running on, it's not state-of-the-art. I built it, I think in, like, 2021 or something, a few years ago. It's not a pushover, but it also it's not state-of-the-art. It can do a decent amount of work. But I wouldn't expect, modern games to run on it at full throttle. And oftentimes, not always, but often, poor performance is not due to the computer being bad, but the software being bad. It's doing a lot of extra work that it doesn't actually have to do to deliver those data transforms and deliver the stuff to the player. And you could say that the information density is extremely low. We're taking up a lot of memory for basic things, and we're constantly pushing stuff out of the cache. We could be just loading the cache to read a single piece of information, and we're also asking way too much of the GPU that isn't necessary for the game. So the barrier to entry for modern gaming is very high. And even on consoles, like the Xbox One couldn't even run Cyberpunk when it came out. And there were versions of that console specific to the release of Cyberpunk 2077. The console that was exclusive to that game could not even run it. That's how bad it was. So what we're doing is we are trying to be inclusive. We want everybody to enjoy the games that we make on any type of hardware that they have, within reason, right? So we don't want to say this can only run if you have extremely expensive hardware. That's essentially what you're saying. Throw more money at it. Get a better computer. Get one that can chug away at those cache misses per frame, or get a more powerful graphics card that can do all the things at once, because we haven't. We're saying it's all necessary. We can't turn things off. We're going to stutter because you don't. It just get a better graphics card. Well, let's try to do some calculations up front to prioritize critical routines to calculate the minimum amount of work and the minimum amount of resources we need to run the game. And in a lot of cases, that number can be staggeringly low. Modern computers today are extremely fast compared to computers of like 10 years ago. Multiple orders of magnitude. There's a really good talk by Casey Muratori on what's it called? Clean Code, Poor Performance, I think, where just doing things like in a typical like object-oriented abstract way can, like at scale over time, can erase a decade and a half of hardware evolution. and doing simple optimization strategies. I'm not talking about like super hardcore stuff like replacing certain routines with assembly or SIMD. We'll get to SIMD like probably later on. That is a little bit more advanced, but just doing basic things like doing the base amount of work to transform our data, how it needs to be transformed without doing any of this other nonsense. We can astonish the player at how fast their computers actually are within reason. If they're doing something weird like running multiple games at once and streaming it, I don't know what to tell you. You're the one who is poorly utilizing the resources on your machine at that point, not me. And let's say if they are running on like an older machine. They got a cheap machine from Walmart or something, a dual core with like, the base 4 gigabytes of memory. There's not a whole lot of threads that we can create at once. Worst case scenario, the player will face a few more loading screens, loading times, and sacrifice some polished graphics and simulation type stuff. But they can still experience a seamless story as the game is running. We make use of what we have as best we can to deliver a solid player experience. That experience may not be as polished as it can be if they're running on older hardware, but there is no reason whatsoever that games should be performing badly in 2024. So, that's all I got. It was a little bit more long-winded than I wanted, but in part 2, if there is a part 2, whenever there is, I want to focus on It Flies By, but this has been a thing on my mind for a little bit, and I want to sort of record it for future reference. Later on, when I have some bandwidth free, this could be in several months from now. I don't expect this to be soon, but I'd like to do some experiments on calculating those theoretical and actual performance characteristics, like what we can reason to be the amount of cycles per frame that we can use, and how we can go about calculating that in really simple ways without getting really pedantic about things. So, thanks for watching, and I'll see you next time.